The real numbers, well, they have the structure of a group, but there's an infinite number of them, a continuously infinite number of real numbers, so it's sort of like a continuous group. The real numbers are a group with respect to the operation of addition, but not the entire real numbers are a group when the operation is multiplication. We have to divide it into two different parts. There's the positive real numbers, and then that's going to be the same as the negative real numbers where we just have a minus sign, right? So in other words, the real numbers are not closed under multiplication unless you can just get rid of zero. If you're just sitting there multiplying real numbers together and then you go to the bathroom and when you come back someone has multiplied all your numbers by zero, then you just lost all the information that you had from all that work you were doing multiplying the numbers from before. Once you're at zero, you can't multiply it by another number to get back from zero, you're stuck. So we had to get rid of zero and delete it. But then when we did that, there were just these two parts, the positive and the negatives. And if we ever did a positive times a negative, we would have teleported from the positives to the negatives, but we can never just walk from the positives to the negatives because there's no zero there anymore. There is a grand conspiracy to force the logarithm to not work at zero for this reason. But we could just multiply the logarithm of anything by -1, and then use the rules of logarithms to bring the -1 upstairs. But when you bring a -1 upstairs, you have to take that number and bring it downstairs. What's nice about the logarithm is that it's what's called a homomorphism, or in other words, it preserves the group operation, and it's an isomorphism, which means that it maps elements of one group to elements of another group. And so the logarithm and the exponential function, which are inverse functions to each other, they're homomorphisms, which let you go back and forth between the operations of addition and multiplication. The real numbers have this dual nature. They're a group with respect to the operations of addition and multiplication. And the exponential function is a mapping, which allows us to move between those two ways of viewing the group of real numbers. But the thing is, you can also use addition and multiplication to create polynomials. And when you do that just using real numbers, if you want to factor them, the only way you can do it is by using complex numbers. There are two perspectives for looking at the roots of the polynomial. On the one hand, we can ask the question, how many roots does it have in a given region that's closed in the complex plane? But then we can also ask the question, for a given interval, how many real roots does the polynomial have? And to answer that question, we're going to need to look at the algebraic structure. The reason we need to look at the algebraic structure and use the polynomial division algorithm is because we're really looking at the intersection of two polynomials. The real line is just the equation y equals 0 in the complex plane. And that's a polynomial, right? If you're just kind of like sitting around and someone hands you a polynomial and says, can you count the number of real roots? And then they also give you this closed interval and they would say, how many real roots in this closed interval? Then how can you do that? To do that, you need to know how to count the number of intersection points of the polynomial y equals 0 with this other polynomial that someone just handed to you. What we're going to do, just for fun, is make things even more complicated for ourselves. Instead of x and y, we're also going to bring in this other variable z. And then just instead of counting the number of intersection points, we want to actually look at these two surfaces in three-dimensional space that are intersecting with each other. An example of a polynomial in 3 variables is x squared plus y squared plus z squared minus 1 is equal to 0. That's a polynomial, and its solution is the surface of a sphere. Whereas polynomials in one variable, their solutions are just a distinct set of points. When we have more than one variable in our polynomial, our solutions are going to be surfaces. What we are looking at is actually the intersection of the surface of the sphere with the xy plane as the sphere is passing through the plane. But the thing is, what we're actually looking at right now is that there's a cone and the ceiling is moving up. So we're actually watching the ceiling moving up through a cone. And we just thought it was a sphere going through the ground. So if we're just looking at this picture of a circle, how can we decide if this circle is really a cone going through the ceiling or a sphere going through the ground?